Hello everyone, and welcome back to this sequence on trigonometry. And in this video, we're going to talk about the angle, sum, and difference formulas. We already talked about some formulas involving, say, cosine of theta plus pi, or cosine of theta plus 2 pi, or cosine of theta plus pi over 2. But in this video, we're going to deal with alpha plus beta, sine and cosine of alpha plus beta. And so for the first part, we're going to come up with what the formula is, and it's a little bit of a trickier geometric derivation than we've seen before, but we'll then go on to then actually state what the sum and difference formulas are, and then go through some example applications of these formulas. Okay, so the goal is to understand cosine of alpha plus beta and sine of alpha plus beta. See if we can get it in terms of cosine and sine of just alpha or beta alone. And so in this picture over here, what I have is this angle here, which is alpha plus beta. And we have this point P. And the way that I can see, or a way that we can see how to figure any of this out, is that first of all, there's this angle alpha, which is this blue line. And then there's also this angle beta, which is now this orange line. And so x-axis to x prime, that's alpha, and then x prime to the orange line, that's beta. So we're going to try to deal with two different coordinate systems simultaneously. We were doing that back when we were thinking about rotation by 90 degrees. But now it's a bit trickier because it's some angle alpha that we're going to rotate things by. Right, so here's what you should keep in mind. So we're going to imagine that we have this point P, and we're going to try to figure out how to rotate things by alpha. Okay, so here's how we'll organize it. First of all, we've got the black coordinate system with xy coordinates, and then there's also another coordinate system that's rotated by alpha, and that's the x prime, y prime coordinates. So in the black coordinates, the point P is it's an actual angle of alpha plus beta. So it's cosine of alpha plus beta, sine alpha plus beta. Those are the x and y coordinates of P in this coordinate system. But in this blue coordinate system, it forms an angle beta with respect to the x prime axis. And so there it's simpler. It's just cosine beta, sine beta. That's the point P with respect to the blue coordinate system. So what we need to do is try to figure out if we have a point in the blue coordinate system and we have its coordinates, what will the coordinates be in the black coordinate system? So let's imagine that we had a point AB in the x prime, y prime coordinate system. So what does that mean? So let's draw a picture. Here's our x prime, y prime coordinate system, and we've also got an xy coordinate system, and we've got a point, say, AB. So to be a point AB in the x prime, y prime coordinate system, that means that we go along the x prime axis by a units and then go in the y prime direction by b units. So a units in the x prime coordinate direction and then b units in the y prime coordinate direction. If we know which way x prime is pointing, then we can figure out what contribution each of these or the a part is contributing to the actual coordinate in this system, and then if we know which way y prime is pointing, we know the other one. So we do know which way x prime is pointing. So the x prime is given by this angle alpha, and its x coordinate is cosine alpha and its y coordinate is cosine alpha. And then there's also the y prime axis, and we already figured out in a previous video that if you rotate by 90 degrees counterclockwise, it's minus sine alpha cosine alpha. Okay, so this might be a bit of a jump if you haven't seen this before. And if you go on to take linear algebra, then you can explore this a lot more deeply. And also understanding this, it's one of those things where if you can understand it now, it is helpful when you need to deal with all these different coordinate transforms, if that is what is in your future. So we want to go a in the x prime direction, and x prime is cosine alpha sine alpha. So in the black coordinate system, we have a times cosine alpha, a times sine alpha. Those are contributions to the x and y coordinates in the black coordinate system. And then we're also going b in the y prime direction. Y prime is minus sine alpha cosine alpha. So then we add to it the contribution to that from that, which is minus b sine alpha plus b cosine alpha. Okay, so this is the formula for given a point AB in the blue coordinate system, what is its corresponding coordinate in the black coordinate system? We know the point P in the blue coordinate system. That's right here. And so with A equals cosine alpha and B equals sine beta, we can plug it into this formula like so. And then we can now just summarize. So on one hand, we know the point is cosine alpha plus beta, sine alpha plus beta, and through all this analysis, we got this other expression. So equating x coordinates and equating y coordinates, we have that cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta, and sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Memorizing this one is a bit trickier, I find. And so it's cosine is cosine cosine minus sine sine, and sine is sine cosine plus cosine sine. So I always remembered that with cosine, it's cosine, cosine, sine, sine, and then it's negative if there's a plus. And then for sine, it's sine, cosine, cosine, sine, and it's a plus if there's a plus. Okay? From this, we can get some other identities. So these are the angle sum identities, but we can also get the angle difference identities. So cosine of a difference of angles. So we plug in negative beta in for beta. So I just plug that right in. Cosine of a cosine's even, so the minus sign we can wash away. But then sine is odd, so the minus side comes out and then turns that minus into a plus. Similarly, we can do the same thing for sine. We plug in negative beta in for beta in the angle sum identity. Cosine is even, minus side washes away, and sine is odd, so the minus sign comes out and turns that plus into a minus. So in this case, for these identity mnemonics, we've got cosine of minus is cosine cosine plus sine sine, and sine of minus is sine cosine plus I meant minus cosine sine. So in general, actually, it's that cosine of plus or minus is cosine cosine minus plus sine sine. And sine of plus or minus is sine cosine plus or minus cosine sine. So cosine has the opposite sign, sine has the same sign. Where the sign in that case is SIGN. A little confusing. Here's another identity you can get from this, the double angle identities. So cosine of 2 theta, that's cosine of theta plus theta. So we can apply the angle sum identity to get cosine cosine minus sine sine, and that's cosine squared minus sine squared. So that's one way to write the cosine of 2 theta. It's pretty common to use the Pythagorean identity for cosine and sine. So, sine squared is 1 minus cosine squared. So we can write it instead as cosine 2 theta is cosine squared theta minus 1. We can also eliminate the cosine squared if we wanted, and write this as 1 minus, there should be a 2 there. Okay, 1 minus 2 sine squared theta, if I got that right. Let me just check for a moment. So I'm putting in 1 minus sine squared here. Yes, that is correct. So sine of 2 theta, that is sine cosine cosine sine with the same plus. So this is theta plus theta. And so that's 2 sine theta cosine theta. Okay, so we've got these double angle identities. Let's do an application of this. We can try to calculate cosine of pi over 8. So the idea is that we can use this cosine of 2 theta equals 2 cosine squared theta minus 1 formula to get a formula for pi over 8 using pi over 4. So let's plug that in. So here's our double angle formula. So plugging in pi over 8 gives us cosine of 2 times pi over 8 is 2 cosine squared pi over 8 minus 1. And then since cosine of 2 times pi over 8 is cosine of pi over 4, that's one of the angles that we know. I get cosine of pi over 4 is root 2 over 2. And so plugging that in, we have root 2 over 2 is 2 cosine squared pi over 8 minus 1. Let's add 1 to both sides, divide both sides by 2 to get cosine squared pi over 8 by itself, because then we can take the square root of both sides to get that cosine of pi over 8 is either the positive or the negative of the square root of this quantity. Now, it's not both plus or minus. Cosine is just a single value. It's one of them. And so for this, we can analyze that since pi over 8 is in quadrant 1, that's where cosine is positive, so it's the positive value. So there we go. Cosine of pi over 8 from this identity. Let's do a follow-up, which is let's calculate cosine of 3 pi over 8. So what we can do is identify this as 3 pi over 8 is equal to pi over 4 plus pi over 8, and use the angle sum identity. So it's cosine cosine. That should not be a plus. That is a little mistake. Because remember, cosine always has the opposite sign. So cosine cosine minus sine sine. And then pi over 4, that's a place where we know both cosine and sine. They're both root 2 over 2. From there, we can factor out the root 2 over 2 for just so that there's less writing. And so now it's root 2 over 2 of cosine pi over 8 minus sine pi over 8. And because pi over 8 is in quadrant 1, we have this identity that sine of theta is root of 1 minus cosine squared theta. This is from solving for sine of theta and then taking the square root of both sides using the Pythagorean identity. And then it's quadrant 1, so it's the positive value. So we plug that in. And we already have cosine of pi over 8 from before. So we can plug that in and then get a value. And then now we know what cosine of 3 pi over 8 is. So as you can see, this angle sum identity is it has the capability of giving us the values of a whole bunch more sines and cosines, exact values. So as an aside, one thing that we can notice with this double angle formula is now that we know cosine of pi over 8, we can also get cosine of pi over 16 by plugging pi over 16 into this formula and then doing the same process. And then we can do pi over 32, that's 2 times 16, and then pi over 64, pi over 128, and so on and so forth. So we can get pi over all powers of 2, and we can do both sine and cosine using similar techniques. And then we can also use the angle summation identities to then use all these values that we calculate and approximate the cosine and sine of any angle to any precision. The idea is that you rate the angle in binary, basically, and you use these to turn that binary representation into the sine and cosine of the angle using the angle summation identities. And you can look this up on Wikipedia or on the internet. This is the principle behind the quartic algorithm, which a lot of digital computers use for calculating sine and cosine. This is the coordinate rotational digital computer. And in fact, this is something that if you have enough time on your hands, you could create tables of sines and cosines of all of the angles that, or of any angle you want to any precision. Okay, so let's finish. So now we're in the last phase of this video. We're going to solve a few problems. So the first one is, we saw this identity from an earlier video, cosine of pi over 2 minus theta equals sine of theta. So now that we have the angle difference formula, we can apply it directly. So this is cosine of pi over 2 cosine theta plus sine of pi over 2 sine theta. And cosine of pi over 2, that, this is a right angle, so that's pointing straight up. The x value is 0, the y value is 1. And that leaves us with sine. So this is the, the complementary angle identity, and we can get it using the angle difference formula. Okay, so another thing that these can give you is ways to combine sines and cosines into a single trigonometric function. And from that, you can solve some trigonometric equations. So we've got this sum of sine and cosine, and we need to figure out how we might use the angle sum formula. There's the magic way, which is what the book uses, and there's the one that I hope is less magic way. And the magic way is you multiply by a magic number, and it just happens to work. But here's something to notice. We've got sine theta, cosine theta. So let's see. Oh, right. I think I have to do the magic. So the idea is that we want to find an alpha such that basically, let's see. So we want it to look like sine theta plus cosine theta somehow. So let's write this as sine alpha cosine theta plus cosine alpha sine theta. And to get these to be equal, so we look, it's 1 and 1 in front of each of these. They're equal. So we want sine alpha to equal cosine alpha at least. This happens. We just need some alpha where this works. So one that comes to mind is pi over 4. So in that case, we get root 2 over 2 cosine theta plus root 2 over 2 sine theta, which is equal to root 2 over 2. And I'll write that as sine theta plus cosine theta. And so, I'll move this over a little bit. We see that sine theta plus cosine theta is equal to 2 over root 2 of sine of alpha plus theta. So I'm taking the fact that sine of alpha plus theta is equal to root 2 over 2 sine theta plus cosine theta. I'm dividing both sides by root 2 over 2. And I get this formula, which is, so 2 over root 2 is also known as root 2. And so our equation is root 2 sine alpha plus theta equals 1. Oops, right. I've been using alpha here. I'm going to use, instead of alpha, I'm going to actually use the actual angle that I chose, which is pi over 4. And that is equivalent to sine, let's divide both sides by root 2, because when you're solving a trigonometric function, you want to isolate the trigonometric function. Okay. So now that is our equation that we want to solve. And now what we need is the ability to graph this. Well, let's see. There are a few ways that we can try to do this. Maybe let's just graph it. So this is a sine function with a normal period, which is 2 pi, but we're shifting it by pi over 4. So pi over 4, it goes up, down, back up, and then, so this is at minus pi over 4, and then this is at 2 pi minus pi over 4, and then 2 pi half. Let me correct that a little bit. That looks bad. So it comes up and then back down. So here would be 2 pi. So shifting the whole sine graph to the left by pi over 4 units. And it comes up to 1 and down to minus 1. And we want to know, when is this equal to 1 over root 2? So that's at about, well, actually, it happens right at 0, as it turns out. So here's root 2 over 2. We want this point, and that point. So, okay. So when theta is 0, we get 1 over root 2, which remember is the same as root 2 over 2. And so we know two of the solutions already, 0 and 2 pi. And we just want to know, where's that one? And the way that, let's see, how can we see what that is? Like there's a lot of ways to try to explain this. But what I'm going to say is that, let's see, like this distance and this distance are the same. And let's see. Minus pi over 4. So remember, 2 pi is the full period, and the distance from minus pi over 4 to here is pi over 2. And so this distance right there would be pi over 2 minus pi over 4, which is pi over 4. And actually, it turns out that this, and this are all the same length. So that means that this must be at pi over 2, which would be pi over 4 plus pi over 4. Okay, so the solutions, and remember, we were trying to solve it using for all theta from 0 to 2 pi. So the solutions are 0, pi over 2, and, well, 2 pi, we don't need to include it because that is not in our interval. Let's not include it. So there are actually only 2 solutions to this. Now let's check our original equation to make sure this makes sense. So it's sine of pi over 2. Sine of pi over 2 is 1, and cosine of pi over 2 is 0. And so great, that's a solution. And our other solution was at 0. And at 0, cosine is 1 and sine is 0. So we get 1. So I guess we could have found both of these solutions right at the beginning, but at least we used the angle formulas to find a solution. And this is somewhat more general. Okay, so let's use these techniques to solve this one. And let's add in for 0 less than or equal to theta less than 2 pi. So here is how you can do this in general. What you do is if you have a sine theta plus b cosine theta, what you want is a magic number, and that magic number is some scaling factor that you can divide by to make it so that, let's see, so we've got this. What you do is you divide by root a squared plus b squared. And we have 1 over root a squared plus b squared sine theta plus, a over that, b over root a squared plus b squared cosine theta equals c over root a squared plus b squared. Then find alpha such that cosine alpha is equal to a over root a squared plus b squared, and sine alpha is b over root a squared plus b squared. And then what do you do? Well, then this is so cosine alpha sine theta plus sine alpha cosine theta and then you can apply the formula for sine of alpha plus theta. and solve for theta. Okay, so let's look at our problem. So we have, what was it? It's sine theta minus root 3. Sine theta minus root 3 cosine theta is 1. Okay, so a is 1, b is root 3. A squared plus b squared is 1 squared plus root 3 squared, which is 4. And square root of a squared plus b squared is 2. So, divide by, root a squared plus b squared, which is 2. And we have 1/2 sine alpha minus root 3 over 2 cosine alpha, or theta is 1. Oh, not just 1, 1/2. Then we can, let's plot this on a unit circle. So, and by the way, the point of dividing by root a squared plus b squared is then that guarantees that the two coefficients here, that a over root and b over root, are a point on the unit circle. That's the whole point of this. So, so 1/2 is right here. Root 3 over 2 is right, negative root 3 over 2 is right there. So this is 1/2 minus root 3 over 2. So we want to know, this angle. That's alpha. So I think, well, we can look at a table for this. And I believe, let's see. So I think it's 5 pi over 3. Yes. So that gives that cosine of alpha is 1/2 and sine of alpha is minus root 3 over 2. So in particular, we can write this as sine of 5 pi over 3 plus theta is equal to 1/2. So I'm going to show you now a slightly different way of solving this sort of problem. So sine, let's use a new angle. Let's use gamma. Or I'll just use x. Sine of x equals 1/2. Well, okay, we're trying to solve this with x equals 5 pi over 3 plus theta. If we solve this for x, then we can solve for theta. That's the idea. And, okay, so here's sine. We want it to equal 1/2, so there's two solutions, at least in the interval from 0 to 2 pi. And what are these? When is the sine equal to 1/2? So when, let's just say x is in here, the solutions are x equals pi over 6. That's this first one. And then the other one is pi minus pi over 6 because of this symmetry. That's pi. So pi minus pi over 6 is 5 pi over 6. Because I don't trust myself to do this, just checking a table. Enabling my calculator. Great. So it's periodic. What we can do is we can say that the solutions are x equals pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k for all k in the integers. So we haven't discussed this. These are the integers. Integers are whole numbers, and they consist of all the whole numbers, positive and negative. Okay, so if you don't care about just being inside 0 to 2 pi, then there are infinitely many solutions by adding in multiples of 2 pi. Okay, so here's where we are now. Theta is equal to x minus 5 pi over 3. So it's equal to, we just plug in our solutions. We've got pi over 6 plus 2 pi k minus 5 pi over 3. And 5 pi over 6 plus 2 pi k minus 5 pi over 3. And let's simplify that. So let's see. 1/6 minus 5/3 is minus 9 pi over 6 plus 2 pi k. And 5/6 minus 5/3 is minus 5/6, 5 pi over 6 plus 2 pi k. Yeah, and so this double z is kind of like a bold z. In some older textbooks, it really is just bold. But this is how you can write bold text when written. Okay, so our original goals, we want to solve this equation for all theta in this particular range. So we found all theta. This is the full solution set, but we want to know only those solutions that are in the range 0 to 2 pi. And to do this, it's really a simple matter. Let's simplify this a bit more. So this is minus 3 pi over 2 plus 2 pi k. And this is minus 5 pi over 6 plus 2 pi k. So we want to get them in this range. All we have to do is add multiples of 2 pi to get it in the correct range. So minus 3 over 2. If we add 2 to that, pi, we get pi over 2. And minus 5 pi over 6, we just have to add 2 pi to that one also. And that is 7 pi over 6. So there we go. Solutions consist of just pi over 2 and 7 pi over 6. Let's make that curly brace nicer. So why did I only add 2 pi? The idea is that if I were to add 2 pi again, I'd go outside the range. And 2 pi, this is the only multiple of 2 pi that gets us into that range. It's just like the comment about phases in a previous video. Okay, this is probably explained in more of a complicated way than necessary. Apologies for that, if so. And anyway, that was that for this video, and I'll see you next time.